x is the value observed. When I roll the die, there's 6 possibilities. So the space for x is what can I observe? There's 6 possibilities, right, for what can I see. The random variable x is whatever comes out. Now the probability of x is for any value that's 1 over 6. Because this is a pair die, that means uniform probabilities for any value to come. How we define mean? So we said mean, these 3 things are the same in terms of random variables. Mean or average or expected values. Sometimes you're going to see a lot in math books this notation, mu. The Greek letter mu usually stands for the mean. It's not a requirement to write mu. Some people write m, some people write x bar or something like this. And the most common notation is this. Expected value of x. Right. Nobody else can stop. Yes.
Should we be concerned with each difference between mu and x bar?
I guess it depends on notation. This is a universal notation that certainly means the expected value. In terms of actual symbols like mu or x bar of m or m of x, it depends what the notation is. Not everybody uses the same notation, but this is always the expected value. So this is, you can think of it as a weighted average, weighted by probability. So in the case of my die here, is probability of seeing the value 1 times 1 plus probability of seeing the value 2 times the value 2 plus probability of seeing the value 6 times value 6. Sometimes I'm just going to write this P of 1 times 1 plus P of 2 times 2 plus P of 6 times 6, which is mathematically incorrect. We are abusing the notation here. In context, this is going to be probability of seeing the value 1. But if you go to a math book, they probably going to say that that's not the right way to write the notation. Or as a sum form, we can write it as a sum for all the values from 1 to 6. This is all possible values of probability of that value times the value. Of course, in the case of the die, this is actually 1, 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 3.5. This average, which is a weighted average, is actually the arithmetic average in this case because the probabilities are all equal. So 1 over 6 creates an arithmetic mean. How many people with me so far? Good. That's the basic average. Now, of course, if my die is not uniform, let's do a variation here. Die not fair. That is not uniform. Let's say the probability space is the same. I can still see any one of those 6 values. But the probabilities, I'm going to write this as an array. For 1 is, say for 6, it's about a half. Let me write this again to make it more clear. 1, 2, 3, 4, 5, 6. And let's say the probability space is for 6, it's about a half. Sorry. Now that's much bigger than a 1/6, right? So this die, if I throw it, I'm more likely to get a 6 than other values because it has been faked, has a little metal piece on it. So when you throw it, it has a metal piece on 1, so 6 stays on top, right? So the other ones must do what? What's the condition of a probability space? Must what? Add to half, right? Because the whole thing has to add to 1. The probability space must add to 1. So let's say we have 0.1, 0.1, 0.1, 0.1, 0.1. That would be here 0.5, it's 1/2. Now this die is not uniform, so if I compute the expected value now, I get 0.1 times 1 plus 0.1 times 2 plus 0.1 times 3 plus 0.1 times 4 plus 0.1 times 5 plus 0.5 times 6. That's the big value there. So this is 0.1 times 1 plus 2 plus 3 plus 4 plus 5 plus that is a 3, right? So now how much is 1 plus 2 plus 3 plus 4 plus 5? 15 times, so the 15 times 0.1 is 1.5 plus 3, that is 4.5. Means this die on average produces bigger values than this die.
Yeah.
Because the 6 is more frequent in there. Let's do another one, the opposite die. How about we have space, again, this is 1, 2, 3, 4, 5, 6, and now the probabilities are the opposite. It's 1/2 here, and the 0.1, 0.1, 0.1, 0.1, 0.1. So that's a very low die. The frequent value here is what? 1. Half of the time, I'm going to get a 1. And the other half of the time, I'm going to get one of these values. So in here, the expected value, similarly to here, is going to be 1/2 times 1 plus 0.1 times 1 plus 2 plus 3 plus 4 plus 5. No. 2 plus 3 plus 4 plus 6. Sorry. So how much is that? That 0.5 coming from here. 2, 3, 4, 5, 6 is how much? 20 times 0.1. So 2 plus 0.5 is 4.5. On average, this is a low die. That's a fair average die. This is a high die. That's the principle of how expected values work. It's an average, but it's not an arithmetic average of values. It's a weighted, where every value, it comes in the average with its weight, the probability. The more likely that value is, the more it contributes to the average. In here, half of the average comes from 1. The other half comes from the other values, because the total weight of the other guys are 0.5. In here, half of the weight comes from the 6, and then the other half overall comes from the other values. Okay? What if we have 2 die uniform? So the x value I'm looking for is a random variable. I may say sometimes random variable. So these let's put it big. Is the sum of the row. So what can I get in a sum if I throw 2 dice? What are the possible values? What's the minimum I can get if I roll 2 dice? 2. I can get 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right? That's the possibilities I can get. Now, what's the probability space? If I roll 2 dice, in how many ways can I get? How many possible rolls are there altogether? If each die has 6 possibilities. 36 possibilities, right? So 36 possible rows. That's in order. That's kind of die 1, die 2. So that's 36 counts 1, 2, and 2, 1. It's 2 different rows, or 3, 6, and 6, 3. So in how many ways can I get a 2? That's only one way, which is what way? 1, 1. How many ways can I get a 12?
1.
It's only one, which is coming from where? 6, 6, right? How many ways can I get an 11? Which are the 2 ways I can get an 11?
5, 6.
That's 2. How about 10? How many ways can I get a 10? 4, 6, 5, 5.
3, 7.
Hmm? How many ways can I get a 10? What are the rows that give me a 10?
4 ways.
3 ways.
4,
Oh no, 3.
4, 6, 5, 5, and 6, 4. So 5, 5 is only one way.
Yeah.
So that's a 3. How about
If we're counting 6, if we're counting 5, 6, and 6, 5 is different, then we should count 6, 6, and 6, 5 is different. Like, it's like one.
Yeah.
So,
so this is
should be 2.
5, 6, and 6, 5, the 2 ways,
Yeah,
right?
but then also 12 can be 6, 6, like 6 from the first die, 6 from the second die.
And
Or 6 from the second die.
isn't that the same?
But
Yes.
technically it's like, it's not just, because we're counting 6, 5, and 5, 6 is different with like order.
So I have a red die and a blue die. I roll it down. I see 5 on the red, 6 on the blue.
Yeah.
Another way is to see 6 on the red and 5 on the blue.
Yeah.
But when I roll 6, 6, I must see 6 on both of them.
Yeah, but
There's only one way. Reversing it still gives me 6 on the blue and 6 on the red.
okay.
That's a good point. You can trust me on the numbers, but you should think about that. Why 6, 6 is only one possibility, while 5, 6 are 2 possibilities. And if you really don't believe the math, you should take 2 die, physical dice, roll them, 1,000 times, and see that 5, 6 happens more often than 6, 6, because could be either way. 6, 6 requires an exact count on each die, 6 and 6. 5, 6 can happen on either 5 on red, 6 on blue, or 6 on red, 5 on blue, which is going to appear more often. So same thing here, I have 3, 4, 5, 6, 4, 5. Is that right? 7 can be obtained in 6 ways. 1, 6, 2, 5, 3, 4. What's the next one? 4, 3, 5, 2, 6, 1. The 6 ways. Of course, now those are probabilities, so they're all divided by what? 36. Do they sum up to 36, those counts? Because if they don't sum up, we're in trouble, right? They have to sum up to 1. 1 plus 2 plus 3 plus 4 plus 5, that is 15. That's another 15 from here. 1 plus 2 plus 3 plus 4, 5, 5. 15 plus 15, 30. Plus 6, 36. So they do come up. So what's the expected value now on x? X is the sum. That's going to be the value 2 times probability of 2 plus the value 3 times probability of 3 plus all the way to 12 times probability of 12. So if I sum up this, I get 2 times 1 over 36 plus 3 times 2 over 36 plus 3
No.
2, 4. 4 times 3 over 36 plus 12 times 1 over 36. So let's do this calculation. There's 36 in the front, 1 over 36. This is 2 times 1 is 2. 3 times 2 is 6. 4 times 3 is 12. The next one is 5 times 4 is 20. Plus 6 times 5, 30. 7 times 6, 42, 8 times 5. How much? 40. 9 times 4. 10 times 3. 11 times 2. And 12 times 1. How much is this? Again, 1 over 36 is common factor in the front of this sum. 2 times 6, 2 plus 6 plus 12. Oh, yeah, 70, 112, right? 152 plus 36, 188 plus 30, 218 plus 22, 240 plus 12. Let's say 252. Can anybody do this calculation? How much we get? 7. So the average value of throwing 2 dice and getting it's a non-uniform probability. Obviously, not all values are equally likely. When you throw those dice, you're much more likely to see stuff with high probability like 6s and 7s and 5s. These guys in the middle, because there may more ways to obtain that value, they're more likely. And these value at the extremes are less likely. In many games, these are particular values, 2 and 12, that have a meaning. It's very good or very bad, and they are very rare, those events. The ones in the middle are more likely to happen when you roll a die. The average of such a die is 7. Average matters when how much you roll has to do with how much money you get from the bank, Monopoly games and so on and so forth. So then the higher the average of your rolls, the more money you're likely to get in the long term. So that's about die. And the other problem that we were just, I think that's the last thing we did, was to say we have coin tosses. We have a sequence. And so the probability space, so one coin toss, it's either heads or tails. This is called heads of the coin, that's the tail. Now, 2 coin tosses can be what? I can get head, 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 tail, tail, head, and tail, tail. As a sequence, if I do 3 coin tosses, I can get head, 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 tail, head, tail, head, head, tail, tail. How many options are here if I toss a coin 3 times? 8 possibilities. So this is 2, this is 4, this is 8. Now what we care about in here is a random variable, which is the number of heads. So we don't really care about the sequence, which one of those sequences is, but we care about how many heads you got in there. So in that sense, how many heads are here? 3. How many heads are here? 2. Is there any sequence with no heads at all? Yeah. Which one is that? Tail, tail, tail. That's a 0. So what I want to say, I want to throw this coin up in the air n times, where n is a variable to be 100, and I want to know what's the expected number of heads when I do that. Right? So I want to compute expected. This is a random variable, because every time I throw this coin 100 times, I throw it now, I may obtain a number of heads, like 20 heads. But if I throw it again 100 times tomorrow, I'm going to get a different number of heads. And again, the next day, I'm going to get a different number of heads. So on average, how many heads I'm getting on average. How do I do this? I use the expected formula, right? So I say expected value of x is the sum over all possible values. This is number of heads possible of that value, k, times what? What's in the expected formula? It's you sum it over all possible values. The value of the random variable is times the probability to see that number of heads. Sometimes people write this as xk. As they say, that's the value of x for k. But the value is actually k. Right? So don't get confused by that. Now, what is this? Remember the stuff when we counted the binomial and trinomial coefficients? We were saying x plus y plus z at the power. What's the coefficient of x cubed times x squared times e to the 5? This kind of thing happens in here. In how many ways can I get exactly k heads? Right? The sum of these sequences that have k heads and some of them that do not. Probability will have to do with how many sequences have k heads. Right? How many people follow me? So k, how many sequences? If I throw the coin 100 times, how many of these 100 times possible sequences of 100 have exactly k heads? So how do we look at this? Here's the sequence.
It's like 100 choose
Size n. How many sequences? That's a counting problem. Go back 2 weeks, okay, in time. We're not a probabilist, we're counting now. How many sequences of n bits, right? Those are bits 0, 1. They're not heads and tails, they're bits 0, 1. So how many sequences of n bits have exactly k ones? And choose k. Now, n choose k is the number of sequences, but what's the probability of observing that sequence? So each one of those sequences have the same probability. What is the, so if I tell you the sequence is 0, 1, 0, 1, 0, 1, 0, so on and so forth, right? What is the probability if you think 0 is the tail and 1 is the head? What is the probability that me throwing that coin in the air, I obtain the first 0? What is this probability? 1/2, right? If the coin is fair. So a fair coin means probability of tail is probability of heads is 1/2. Means if I throw a coin in the air, it's equally likely to come heads or tail. Now, my coin is not unfair, it's not fair. Probability of a head is some number, a p, that's 0.3, and probability of a tail will have to be what? If the head is 70% chance, how much is the tail?
30%.
It's 1 minus p, right? They say that's 0.7, sorry. 0.3. Are we following this? My coin somehow has been modified. When I throw it in the air, it's much more likely to show up heads. Just like the die has been modified to give me more 6s. We don't care how it has been modified, but there's a way to engineer a coin to be more likely to come heads. Now, if heads is 70%, tail must be 30%, because they have to sum up to 1. There is no way for the coin to not be either heads or tail when I throw it in the air. Okay? So now what's the probability to see exactly tail, head, head, head? We say this sequence has k heads. N flips, k heads. How many tails will have to be here if out of n flips I get k heads? N minus k tails. what's the probability now to get this tail when I flip? The flips are independent. I flip the coin, I observe the value, I write it down, I take the coin back in my hand. Doesn't matter that value, I flip it again. What's the probability of this tail here? It's not 50 because my coin is not uniform anymore.
30.
Let's say 1 minus p, right? One minus p, 30%. What's the probability of this head here? P, which is 70%. Now tail again, that's 1 minus p. Head, that's p. Head again, that's p. That's 1 minus p. 1 minus p, and that's a p. Are those independent events the flip coins? Is this independent of that, so on and so forth? So what's the probability of the whole thing when we have independent events? When we have independent events, we multiply. So independent events, probabilities multiply. So what's the probability of that sequence? I need to have exactly these k heads and out of n flips. So how many p's are there and how many 1 minus p's are there? How many times this p has to show up? P times p times p times p. Somebody louder, please.
K times.
Hmm?
K times.
K times. P has to show up k times. And 1 minus p, so that's the probability for heads, and 1 minus p is the probability for tails at n minus k. Now, I could write every sequence, and every sequence with k heads will have that probability. See, it doesn't matter where the heads are in this sequence. The probability will be the same. Whether they are all k heads at the beginning or all k heads at the end or somewhat distributed, there's exactly p k p's from the heads and n minus k 1 minus p's for the tails. So the multiplication of probabilities will be the same even if the heads, the k heads, are in a different position. So all sequences that have exactly k heads have exactly this probability. We feel comfortable with that? If I tell you the following two sequences have the same probability. Here's two sequences. Head, 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 tail, tail. Head, tail, tail, head, head. Head, tail, 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 head. Those three sequences have the same probability. Do we see that? How much is the probability of this? These have to get the head 3 times and the tail twice. And this one, the order of multiplication is different. This one's p times 1 minus p, right? Times 1 minus p times p times p, right? Because it's in that order. But if you do the multiplication, you still get p times p times p times 1 minus p times 1 minus p, right? So even though those sequences are different sequences of flips, the probability on each one of them is the same. The probability only depends on how many heads and how many tails you have. Hands up. This is a phenomena that's essential for counting and flip coins and so on and so forth. That all these particular sequences of 5, in this case, rows, they give you the same probability. Now, that's why we multiply this probability with how many times that sequence appeared. Right? Because all these sequences have the same probability. When I sum them up, I just say it's that probability times this is the number of sequences with exactly k heads and n minus k tails. This number here is exactly how many ways can I get that sequence. So now we need a little bit of algebra to deal with this. A little bit of algebra. We're going to use some tricks here. Let's see if we can get this done. sum from k equals 0 to n. This is k factorial times n factorial, k factorial n minus k factorial, times p to the k times 1 minus p to n minus k. This sounds very close to something, right? It's very close to a binomial where the x is p and y is 1 minus p, right? Remember the binomial formula? Was it what? X plus y at the end? It gives me these coefficients, that and that. What's the difference? So is it going from k equals 0 to n, the binomial formula? Is it from 0 to n? When we open up this, what is the formula here? Sum from k equals 0 to n of n choose k, x to the k, y to the n minus k, right? That was the binomial formula. You guys remember the binomial formula? What's the difference between this and that? N choose k is here, p at k is there, 1 minus p will be y, right? What's the difference? There's something that's not in that formula. There's this k in the front. The k is not in the formula. So we need a little bit of algebra to manipulate this to make it look like a binomial formula. That's just arithmetic tricks, okay? So what I'm going to do, I'm going to observe that if this k would simplify to this k factorial from here, and I'm going to be left with k minus 1 factorial. So I'm going to do the following things. Let's write that down again. So we had sum from k equals 0 to n of k, n factorial, k factorial. I'm going to write this k factorial here as k times k minus 1 factorial. Is that correct? K minus 1 factorial times k gives me k factorial. And now I have the p at k, which I also would like to write p times p at k minus 1 times p at n minus k. Is that correct? P at k minus 1 is p at k. So this stuff in here, it's p at k. So what next? This k goes away with a k, right? And I take in front of the sum, I'm also going to write this n times n minus 1 factorial. Is that n factorial? So I want to write in front of the sum n times p. So out of all the terms, I take the n and the p in front of the sum. Yes?
Why is it e to the n minus k, not 1 minus p? Or 1 minus p to the n minus k?
Very good.
Okay.
That's 1 minus p. Cowboy mistake. What's left of the sum? I'm going to say the k equals 0 term is 0. Is that true? The term that corresponds to k equals 0 is 0 because of this k. So when I do this simplification, I actually couldn't do it for that term because 0 does not simplify with 0. There is a term for k equals 0 in the sum. How much is that term when k is 0? How much is the whole thing?
0.
Why? Because of k. So that term shouldn't be here. I'm just going to say from 1. Who's following me here? This k equal 1 is the same sum because the only missing term in here, k equals 0, that's 0. So when you do this, you have to explain. So what I'm going to put in parentheses here is the k equals 0 term is 0, not in the sum anymore. That's to say, that term was 0, so I can skip it. If I start from 1 the count, I'm just skipping a 0, should not affect my count. Right? So now, what's left of this? N minus 1 factorial divided by k minus 1 factorial n minus k factorial. Right? P is in front of the sum, so that's p at k minus 1, and 1 minus p at n minus k. Right? Again, I took the n and the p, they're in front of the sum, and I didn't write the k equals 0 term because that's 0 anyway. So I can simplify k with k, and then that's what's left. Now what I want to do, this is from k equals 1 to n. Now in here I want to change the index from k to k minus 1. That is, I'm writing the same sum. I'm not changing the sum in any way. But instead of starting from 1, I'm indexing it from 0 now. So every term has to be the same in value. So how would that look? NP, sum from k equals 0 to where? How far do I need to go here? I have to go to n minus 1 because now the indexing has shifted by 1. The nth term in here was from 1 to n. Now it's from 0 to n minus 1. But the terms themselves, the values, are supposed to be the same. I'm just indexing. You know, when you say, here's what this means. You look at the sequence 5, 6, 7, 8, 9, 10. And you say, I want to start indexing not from 5, but from 0. And you say, that's 0 plus, this is the sum from k equal 5 to 10 of k, correct? Is the sum indexing from 5 to 10 of k. Now, how do I write it as, I want to write it as k equals 0 to 6 instead. So I'm indexing it not from 5 to 10, but from 0 to 6. That would be k plus 0 to 5. It's sum of k plus 5 in there, right? So I'm writing it as 0 plus 5, 1 plus 5, all the way to 5 plus 5. It's the same sum. 6, 7, 8, 5, 6, 7, 8, 9, 10 is the same as 0 plus 5, 1 plus 5, so on and so forth. That allows me to index the sum not from 5 to 10, but from 0 to 5. The terms themselves are the same value. So that's what's happened here. I'm going to index this n terms from 0 to n minus 1. N minus 1 factorial stays. Now, who's the first k minus 1 in the first term? If k is 1, how much is this? K minus 1 factorial. It's a factorial this in here. If k is 1, how much is this value? 0. So now what do I put here? It's not k minus 1 because the index has changed. Is what? That's k factorial. And how about here, n minus k? The first n minus k in the first term is actually what? In this sum.
N minus 1.
It's n minus 1. So in here has to be also n minus 1. No, the value has to be remain the same. But the first k is 0 now. If I just say n minus k, how much is this value now? That's n. That's no good because before was n minus 1. So what is the right value here that corresponds to that, but with a different index? See how 8 became a 3 plus 5? What is this becoming to have the same values?
K
Plus 1? This would be n minus 0 plus 1. That's n plus 1 now. Minus 1. Let's also check the last value. When k is the maximum in this sum, what's the maximum k? N. How much is this value?
0.
0. When k is the maximum here, n minus 1, how much is this value? 0. So they correspond, they're the same values. They index differently, but those values are the same. Instead of being counted from 1 to n, it counted from 0 to n minus 1. How many people are still following here? Okay, we can take it more slow. I'm not changing these values of the sum, just change the indexing. I have to make sure every value is the same as before, but now it has a different index. So if the first n minus k is n minus 1, the first n minus k minus 1 here, it's also n minus 1. And if the last value here was n minus n, that would be 0 factorial. In the last value here is for k minus 1, that's also going to be 0 factorial. How about on those p's? What's the first power of p here?
0.
0, so what's the exponent now?
Okay.
Okay. And how about this one? That's 1 minus p. What was the first value here?
N minus 1.
So now this has to be n minus 1 minus k. So I think you should do this exercise. Write the first 2 terms and the last 2 terms, or the first 3 terms on the last 3 terms, and see that they are actually the same in those 2 sums. The indexing has changed, but the value term by term is the same exact sum. Now, this is NP. That's a trick used in a lot of algebra sums, and we're going to study a lot of those in 2 weeks at induction. Changing the index to get a formula the way you want. So k equals 0 to n minus 1. This is n minus 1 choose k times p at k times 1 minus p times n minus 1 minus k. Now this is indeed the binomial formula here. Now for real, this is actually the binomial formula, because I got rid of that k, right? See how that happened? There's no more k. K got simplified, and I worked through algebra. So how much is it? NP in the front stays. What is x and y here? X is who? P, and y, what is this? So it's p plus 1 minus p at what power? This is the binomial formula for what power? Let's look at it. This formula here is for power n. So what do I have here? N minus 1. So how much is p plus 1 minus p? 1?
1.
So that's np, because it's 1 at some power. Now I know this is not easy to solve. Of course I knew where I'm getting with this. It just happened by accident. There's a lot of combinatorial formulas that I know, I have a list of them, and you just find them out. Yes?
So I understand like mathematically what you're doing, I just understand why.
I wanted to compute the expected value of seeing exactly k heads.
Yeah.
So that value is n times p. That is, if you throw the coin 100 times, say n is 100, and p is, what did we say, 0.7? How many heads I'm likely to see in that throw? Expected, on average, 70 heads.
So you just proved that concept.
I just proved this with all these equations. It just happened. Right? Now, this is, of course, an honors proof. The regular section will have no clue what this is. And as a consequence, it's not required for the exams. But I thought it's a cool proof to show you how to use the binomial formula to do this stuff. Now, what I would like to say is to look at this problem and define not one random variable, like I have here this x. I like to define a bunch of small random variables. Here are my small random variables. So again, what is x? This random variable is what? The number of, what is it? If I do what? Heads? If I toss how many coins? N coins, right? So I toss n coins. N is a fixed value, like 100 or 1,000. I toss 1,000 coins. How many heads? And I'm going to see. That's a random value, of course. If I do it today, tomorrow, and the next day, I'll observe different counts. And this is the average count. The average count is out of 100 tosses. So let's write that in English. Out of 100 tosses, on average, there will be 70 heads. That's what this said. You're going to get different counts every day when you throw the coin 100 times in the air, but if you look at the average of those counts, they'll be around 70. Which is kind of what you expect intuitively, right? If it's 70% chance to get a head and you throw it in 100 times, why would it be roughly 70 heads? We just proved that, but intuition is very much common sense here. So here's what I'm going to do next. I'm going to say, how about we define more random variables? So for the same problem here, I have this big X. That's the total number of heads. But how about X1 is a random variable is 1 or 0 for first toss. So 1 means head, 0 means tail. So this X1 is not the sum over the whole sequence. It's just the first toss. When I throw the coin in the air, I look at the first toss. If it's a head, this variable is 1. If it's a tail, it's 0. How about X2? 1, aka head, or 0, aka tail, for what? X2 is going to be heads or tail for what? If this one's for the first toss, X2 will be for the second toss. What is the probability of X1 being a head in that toss? When I toss the first time, what's the probability to get a head? P, right? 70%. And what's the probability of X2 being a head? Also P. Those are independent tosses, right? So I define all these variables up to Xn, and I say this is, again, 1 head or 0 for tails. For what? For the nth toss. So now I have n binary random variables. Each one of them, it's either head or tail. Head will percent 70%, tail 30%. What's the expected value of each one of those? What's the expected value of X1? It is much simpler than this, because that's one toss. How do I compute the expected value? What are the possible values for X1?
1 is 0.
1 times what's the probability of 1?
0.5.
P, right?
Yes.
P is 0.7. So the 1 stands in here for tails, plus 0 times 1 minus P, right? Are we following this? This is a binary random variable that can take values 1 or 0. Value 1 happens to probability P. Value 0 happens to probability 1 minus P. So the expected value is how much? P. That is, the expected number of heads when you throw a coin once in the air is 0.7. Make sense? Or doesn't make sense? Huh?
It makes sense for like a analog point of view.
No, but think about an average. You throw a coin, what do you see?
Yeah.
Head or
Makes
tail?
perfect sense.
You count the 1 head, right? You throw a coin again, you see a 0. You throw a coin again, you see a 1. And again, you see a 0. And a 1, you see a... Now, on average, that's what the expected value means. How many heads per flip you see? It's 0.7. But there's another thing going on here. Can I say my big value x is actually x1 plus x2 plus xn? From a conceptual point of view, can I say the total number of heads you observed over 100 tosses. It's actually whether you observe 1 or 0 head in the first toss, plus 1 or 0 head in the second toss, plus all the way to this. Is that true?
No. No.
So suppose I get a sequence like I show you on the board, head, head, tail, tail, head. How much is the x1 for this value, for the first toss?
Oh, what's the risk?
X1 is 1 for heads, 0 for tails. So how much is for the first toss?
47.
1. So x1, x2, x3, x4, and x5. This is a 1. x2 is what? 1. x3 is going to be 0 and 1. Can I say the number of overall heads observed is the sum of these guys, x1 plus x2 plus x3 plus x4 plus x5? Yeah, because the total number of heads will be counting one head for every time when I see a head. Right? Any questions about this? I feel like I'm losing you guys on this adventure here. Maybe I shouldn't have dressed up as a cowboy today. Wait for the easier lecture. Halloween happened to be on probabilities and expected values. This is lucky, unlucky phrase. All right, let's see how those random variables work out. Huh? My small random variables are 1 and 0 for each toss. x1 is 1 and 0 for the first toss. x2 is 1 and 0 for the second toss, and so on and so forth. So these guys are either 1 or 0. The big random variable is how many heads you've seen total, which is just the sum of how many ones you have. Now, if I do this tomorrow again, I may get a different sequence tomorrow. Tomorrow, the sequence might be, I still do 5 tosses, but I'm going to get tail, head, tail, tail, tail. In that case, how much x1 is? 0. x2?
1. 0.
So how much is x? Can I say x in that case? It's x1 plus x2 plus x3 plus x4 plus x5? Is it correct? The number of overall heads tomorrow is 1 plus a bunch of zeros? Yeah. Well, there is a theorem, very important property, that says if that's true, the expected value of x is, of course, is the expected value of x1 plus, because x is that, but there's a theorem that says the expected value operation distributes over the variables. So that's e of x1 plus e of x2 plus e of xn. So that's a theorem that says the expectation distributes over the sum. Expectation distributes over sum. Every time you can write the random variable as a sum of 2 random variables, you want the expected value of the sum, you can compute the expected value separately and sum it up. So what if we do it this way? Wouldn't that be easier than all these binomial formulas? What is the expected value of every one of these? Didn't we just do that somewhere in here? Expected value of all of them is p. Each one of them is a towing cost. So the expected value is 0.7 p. So this would be n times p, right? Because it's n of them times p. That's where this n times p comes from in here. So if I do this with brute force combinatorics, I get n times p out of binomial formula. But if I do with this theorem that says I can break the expectation into parts, then I can compute the expected value of each one of them. I know that's a p, right? That's p, p, all the way to p. I sum up n p's, I get n times p. Same value as before. Now the problem, this is a lot easier. I know this is much easier than that, but you have to know this theorem. that the expected value breaks into the parts. If you break the random variable into a sum of 3 things, the expectation breaks into a sum of 3 things. And we can prove that formula. It's a very small proof. But unfortunately, we're not ready to understand the proof today. So we can put the formula here, and you're gonna be like, okay, I can read your writing, but it makes no sense to me. So what is that proof? Expected value of x plus y is the sum over all values in the space of xy of value times the probability of that value. That's it. We just proved that the expected value for sum is the sum of 2 expected values. That's correct, but we can't understand it yet. We can understand it on Friday. Because we have to talk about some things between 2 random variables, how these x and y play together. So we're gonna get back to this, and we're gonna understand on Friday. I'm asking you guys to trust me for 3 days in this. But we can verify it on an example. What happens if I run it on this? This thing. So who the x and y is in this problem? Remember when I have 2 die, the red die and the blue die? The big variable x was the sum, but how can I write easily that sum as a sum of 2 random variables? Who would be the 2 random variable if I have 2 dies?
Each die.
Each die. So who's x?
The red die.
The value of the red die. And who's y? Value of the blue die. So what did I get for the expectation? 7, right? I did it brute force. What if I do it with the first die? How much is the first die expected value? Didn't we do that before? A die, when you roll a die, what's the average of it? 3.5. And the other one was? 3.5. So if I sum them up, I get this 7. Right? I could have broken this sum into expected value of the red die plus expected value of the blue die. The theorem says the expected of the sum is the sum of expectations. Then I compute each die separately. I know how much is that is 3.5. That's easy, right? Or 1 die is 3.5. So I could have said this is the expected value of die 1 plus the expected value of die 2. And I wouldn't need this calculation because expected value of a die, I know how to do much easier than this, 3.5. So we're gonna see Friday how this works in probability spaces. But it's an easy thing to remember. For any sum of random variable, no restrictions, no conditions. We're gonna do a lot of theorems that have some condition for them to be true. In this case, there's no restriction. If the variable is a sum of 2 or 3 or 5 things, then its expected value is a sum of those expectations. Like in here, somewhere, we said in order to multiply probabilities, there is a condition, right? What condition is that? The events have to be independent. See, in here there's no condition. Even if the toying causes or the dice would not be independent. They are, right? The 2 dice are independent. They don't depend on each other. The coin flips are also independent. But even if this would not be independent, as in the variable that correlates to each other. For example, the age of a car or the mileage of a car correlates to its year of manufacturing, right? All the cars have more miles on them. You can't say those variables are independent, right? or the age of a person correlates to the income. The older you get, the more money you make. These are not independent things. Even though they're not independent, so these for any x and y, even not independent. We'll see that this works even for events that are not independent to each other. So we looked at a few problems, and what I would like to do now is to show you a more practical side of things. I know some of you just saw probabilities for the first time and expectations for the first time. So I want to run some simulation examples here to put a better sense on what does it mean. Let me do something here. See if we can get this done. Say not here. Okay. I will need one of you to look into the camera monitor to see how much of the screen is being captured, and if it's not enough, you can try to tilt the camera up a little bit. You don't have to go all the way to the top edge of the screen, but the pictures I'm going to show you, you have to capture it. So let's put the picture up first. I have a MATLAB script that what it does, it rolls the die. That's what it does. So I can show you that script. It's in here. It says roll this die once. The one in the parentheses there says roll it once. And when you roll it, hold on, maybe that's not this problem. When we roll it, we get this. This is, you're going to see this a lot. Maybe I should put this down a little bit so you guys can see it better. So in here, these are the counts of what I roll through, and I get this 1 here. So let's make this window a little smaller. So what this histogram says is what did you roll? What value did you just roll? It counts what values did you roll. So whenever you see this bar, means what value did I roll. Values are the x-axis, and counts is on the y-axis. I roll a 4, right? That's why the bar is a 4. And the red is the mean so far, the average. But it's not the average, the theoretical average, it's the average observed. Like I'm actually averaging the values that I see. So what am I going to do now? Roll the die again. So what did I roll now? We can't see. The green one is the last roll. So if I roll a 1, and the x-axis is messed up. If I roll the 1 and the 4, what's the average so far? No, that's not true. The tick is wrong. 2.5, right? Because I have a 1 and a 4, what's the average? See, the red line is pointed correctly at 2.5, but the label, the ticks are messed up. It's not 3. It's supposed to be 2.5 in there. What happens if I roll the die again? What do I get? I got this 2, right? Now what values do I have for my die? 1, 2, and 4. How about again? I got a 6, right? Well, how about now? How about now? Another 6. How about now? A 3, right? How about now? So if I'm rolling this die and I'm keeping the counts of how many times I've got, so how many 6s I got so far? How many 4s? I'll keep rolling it, right? How many 2s I got so far? 5 2s, right? And how many 3s I got? Okay, so I keep rolling. You see, said this is sample size of the title. How many rolls I done so far? And what's my average so far? That is the empirical average. It's not the theoretical average of the die. It's just rolling the die. And the more you roll it, the more the average becomes what's supposed to be, right? If this die is fair, what's going to be the average? There is a theorem that's called law of large numbers that says if you roll the die enough times, as in a million or billion, the average cannot be too far away from the theoretical average if the die is fair. So if my die really was a fair die, if I roll it enough times, okay, let's roll it enough times. What does it mean for the die to be fair visually? Visually, when do you look at these counts, at these bars, and what does it mean to be uniform or fair?
All the bars are the same.
Similar. Doesn't mean, that the bars have to be identical, but they have to be roughly similar. You can't have a very low bar and a very high bar, because that means that high bar is more likely those values to come than the other ones with small bars, right? So now I'm gonna stop this process, because I want to roll these dice not just once. When I roll a die, I want to roll it 20 times. So each press of the key now is not going to roll it once, it's going to roll it 20 times. So this is the last roll, 20, right? I rolled 20, and this is the counts I got, right? This how many 6s I got here? So on and so forth, right? So how about if I keep rolling? It's easier to roll it 20 times at the time, right? And then I get, the last roll, the last 20, it's on the bottom, the green line tells me how much of 3s and how many 5s. Like you see, I only got 1 5 now, and I've got more 3s in this roll. So the average, it's supposed to be 3.5, right? Because this is a fair die, assuming MATLAB works correct. I give it 1/6 probability for each roll. So you can see the average there is actually going, more or less close to 3.5. It can take a long time to be exactly 3.5, but it's guaranteed by the law of large numbers that if you roll it enough time, the average cannot be too far away from 3.5. That's a mathematical theorem. Okay? Sounds like a plan. How about a non-uniform die? So I have here a die that is not uniform. I'm going to take this window out of here. I think you guys understood how the rolls work. I need to see it on my screen. So now I roll a die that's non-uniform. This die, it doesn't have 1/6 probability on every face. So let's roll it a few times and see if we can figure it out. What is the most likely face? So now I roll it how many times so far? 540 times. Okay, so let's say I roll it 2,000 times.
Since 5 you'd see above the average.
Does this look like a uniform die to you? What is the value that seems to be very likely to come up in here?
6.
Out of 2,000 rolls, is this possible for this to be obtained with a uniform die? Possible, theoretically. Is it possible to take a die, uniform, roll it 2,000 times, or how many times?
3,680.
That many times. And get how many 6s out of it?
Over
1800. Is that possible with a uniform die when I roll a die uniform for 4,000 times to get 2,060s? Yes. What's the probability of that to happen?
Low.
It's extremely low, as in 0.000, 100 zeros, and then something, right? So it's not impossible, but if anybody who plays poker or any games like blackjacks or any games with dice, when you see a die roll like this, roll it 4,000 times, it comes 2,060s, you're virtually sure the die is not fair. The die has been modified. The chance for this happening with a uniform die, while it's not zero, it's so small that nobody would believe it. Everybody would be, that's a fake die for sure. Like everybody would bet their life and their kid's life on the fact that this die is not a uniform die.
Wow.
That's how much sure you can be with mathematics. This is not a fair die. Okay? I have another die here. Let me try that.
Is this die
Roll
extreme?
that. See what happens. So this is a die, also modified, not a fair die. It's a different figure now. Okay? So if I roll this die, what do I see?
A lot of ones, slightly less sixes, pretty uniform.
What do we think? So how many times we roll this die now? It's like, what, 3,000 times there or something like that? What do we think about this die?
It's pretty good.
Is it a
The
fair
average
die?
Is the average is
It's not a fair die. What's up with this die?
I think it's
1 and 6.
It's a lot of 1 and 6s. But what's the average of this die?
about 3.5,
Why?
because it's fair.
It's not fair.
I think that's
Why is the average of this die the same average as a fair die, 3.5?
It's like
It's
go
pretty fair.
outwards from the median, the probability.
What would be the extreme version of this die? What the probabilities on 2, 3, 4, and 5 are not zero. You can say there are some counts on those. But if I take this idea to the extreme, what would be this extreme die version? What would be the probability on 6 and on 1? 50-50. And on probabilities in the middle would be what? Zero. If I compute the expected value of that die, I get 1 times 50% plus 6 times 50%. The other stuff is 0. So how much is that formula? 50% times 1 plus 50% times 6 is the average of 1 and 6. So see how this die has the same average as the fair die. If you ask, give me the average of the die, and somebody says 3.5, you wouldn't know if it's a fair die or different. Right? Just by the average alone, you can't tell that the die is fair. Because there are many dice that have an average of 3.5, and they're not fair. Okay? Let's try another die here. What's up with this die? What happened to this die? Yes. It's 3 and 4. What's the average of this die? 3.5. Yet another die that has an average of 3.5, but it's not a uniform fair die. See, I roll it and many times I get 3 and 4. Okay, I need to move a little faster here. Here's the next one. This is 2 die. So I'm rolling 2 dice. This is the bottom line now. The bottom plot. What are those x-axis? Why x-axis has changed on it? It's not 1 to 6 anymore. is what?
Values relative to-
Why is it 2 to 12?
Those are all possible values.
4
Two dice.
The sum of two dice.
is the sum of two dice, right? 2 to 12. So what happens, what do you think is going to happen when I roll these dice, these two dice, and I count how many times I've seen 2, 3s, 4, 5s? This is uniform. Those dice are fair, both of them. What do you think is going to happen? Expected value should go to 7 because we computed that, right? Two ways actually. We computed brute force and we computed as a sum of the two dice, right? But what do you think these plots are going to look like, these bars, these counts, if I roll the die 2,000 times? Somebody else.
Bell curve. Where it's going to go.
You're saying it's going to be bigger in the middle. Why is bigger in the middle?
Because you're more likely to get a 7.
I'm more likely to get 6 and 7 and 8s than 2 and 12s. There's more possibilities for 6 and 7 and 8s. So let's see that. Let's roll this die a bunch of times.
What?
The green is the last roll. And if I roll those two dice, how many times in there? 2,000 times? It's going to look more likely, you see how many values are in the middle? Because every time you roll the die, you're more likely to get 5 or 6, 7 or 8 than you like to get a 2 or 12. How many people understand this principle, that 2 and 12s are less likely here, but the middle values are more likely because there's more possibilities to roll those dice to get a middle value. Therefore, I just rolled this die 2,500 times. To two dice, 2,500 times. This is what I observed. Computers are pretty good at simulation. If you give it a certain probability, like this case uniform, and you roll it, it's actually more random than the nature. If you roll the die 2,500 times, you're not that random. The way you move your hands, the way you take the die, the way you shuffle them is not as random as a computer can do it. Computers can do it more random than humans. So do we believe this plot? The middle stuff has more counts. How about, this is another example. I have 1,000 cars, right? The cars have prices. This is the price of the car, right? So I'm sampling with replace. Anybody remembers from last time what with replace means? Every time I'm sampling 20 cars, I look at their prices, and it's bucketed. Bucketed means I don't plot every single value. Like the dice, I plot the 2s, the 3s, the 4s, that are all the values. Cars now have a lot of different values by dollar. So what I do, I bucket it. See, each bar in here doesn't really mean the car costs $20,000. It's around $20,000. And the values in here are cars that cost about $5,000. So this has been bucketed, the whole price range, which is continuous. Cars can be anywhere from 0 to 30,000, has been bucketed on, say, 1,000 or 2,000 buckets intervals. All the cars in the first interval are from 0 to 2,000. The second interval is 2,000 to 4,000. That's how histograms work. When people build histograms on a continuous range, they don't plot every single value. They bucket it and say all the cars that are around $15,000. Okay? So that's how histograms look like. Now, suppose I sample all those cars. Those are actual real car prices, by the way. The distribution of these car prices, it's the actual distribution in 2016, including, of course, all cars. So what do we observe? If I sample 1,000 cars, what's the average price of a car here? About $15,000 in there, right? And you can see that there are very few cars that were 0. I don't think that's true, but let's say it is. And there's very few cars that were 30,000 as compared to the middle range. Most cars, including the used one, will be around between 10,000 and 20,000. This is typically what's referred as a bell curve that has a lot of stuff around the mean, and it goes on the side to lower counts. So I hope everybody understands. These are the possible values of a car. and the y-axis is the frequency, which is the same as probability, right? Count or frequency or probability are effectively the same thing via normalization. If I divide this count by the sample size, I get the probability for the buckets, right? Do we see this? The x-axis are the values of the cars, the y-axis are the counts, and if I divide the counts by the sample size 1060, I get the actual probability of seeing each price range. Okay. How about coin tosses? What are the possible values for a coin? 0 is the tail, 1 is the head. So if I toss a bunch of coins, where is the average going to be? 0.5, which is half of them are heads, right? But I have here a coin toss that is not uniform. The heads are more likely. This coin toss, it's actually 7% probability on the heads. So what do you think is going to happen if I toss this coin a bunch of times in the air? What's the average now of this coin? This is the coin we just did on the board, that the probability of a head is 70%. If I flip enough time, what should that mean value be? That will go to 0.7, because this coin has a 70% chance of getting a head. So if I flip it enough times, the empirical average, which is how many heads do I notice, it's going to correspond pretty much to the theoretical average. Now, as I said, the mean will take a while to converge. It's not guaranteed to go there that fast, but it's guaranteed in the limit to go there. So the red bar indicates where the mean is. Unfortunately, my ticks here are messed up. I'm going to fix it and put the code online so you can play with it. How about, I have other examples here. I want you guys to guess what this is. So I'm going to run this. There's a mistake here. Oh, what are those?
That's not that bad. Nobody got less than a 50.
So what am I doing here? I'm sitting on a stack of 600 meters. What are the possible values? From 0 to 100, right? And what I just did, I put my hand into the stack and pick out what? 20 meters. So I plotted what counts I have seen from those 20 meters. And what happens if I put my hand in and take another 40 meters? I get more meters, right? And what happens if I
Oh my god.
Wait. I don't think this is accurate.
What's the average of the meter grade in here?
Wait, what happened to the
What's the average meter grade? 76 or so, right? And you can see the actual distribution of the meter grades. Now this is sampling. You remember what with replacement mean? You see that in the title says with replacement? What does that mean? Every time I pick a box of 20, what do I do? Before picking the next batch of 20, I put them back. But I have a piece of code here that does it without replacement. Which means I can do the same thing, except what? When I put them back in,
Alright, so this might actually.
I don't put them back in here, right? This is
That one might be right.
without replacement. That means when I pick the next 20, I have fewer options, right? Because the ones I picked are not put back in. So you can, this process cannot go in forever. The other process, I could have sampled 3,000 meters because every time I sample, I put them back in. But in here, what's the maximum sample size? And how many meters I have? So this will only go up to whenever it can. These are 555 because a bunch of them were not graded when I took this data out. They were late. So these are the actual grade distributions of the meter. How does this compare with, say, a different set? So I'm going to plot here a different set. I'm going to put this code online and ask you guys to play with it. Here's a different set of possible grades for the meter. That's not real. It's not what happens. But what happens here?
Is this just guaranteeing we all get a C?
What happened here with those grades? They have the same average, but there's the same number of students, 600 students in both of them. What happens, what's the case in here? Which means all the grades are very close to 76, the average, which is not the case there. So we need to differentiate those two random variables, which is what we're going to do now. How do we make a difference between a random variable that looks like this and one that looks like that? Where is the difference? They have the same average. It's the same like with diodes. There's this fake dies and real dies. How are they different?
Standard deviation, how far values are on average from the average.
Right. So look at the red line. What he's saying, on average, all these values are pretty close to the mean. On there, the average of any value at random to the mean is much bigger than in here. Right? So what we're going to do is to say standard deviation is the average value to the mean. So normally, you would say, okay, well, what does that mean, average value to the mean? Is the average of how far away is x, it's my random variable, minus the mean of x, right? And maybe you put it in a absolute value, because you want to count the distance, not minus or plus, right? How far away is the random variable to the mean? Say, in here, all the variables are going to be very close. For this distribution, this value is going to be low. But that value is going to be higher. Now, this is what we want, but it's no good math here. So the reason we don't like this formula, while it does what we want, the math on it doesn't work. So instead, we're going to come up with a different average. Is the square root of this x minus e of x squared. Now, you could say, why is this not the same as that? Because this is computed as sum over all x values of that.
If you square root it.
Right, we want the average distance to the mean, that's the concept. But we're going to compute it in a different way. So in order to make this formula work here, we have to average by, so let's just write it as average of this square. And this is the square root of expected of x minus e of x squared. This is the actual standard deviation, and the expression inside e of x minus e of x squared, that's of course standard deviation squared because I just eliminated the square root. That has a name too.
Variance.
Variance. So in principle, we want the distance to the mean, but there's many ways to compute that average. And the arithmetic average of distance to the mean, it doesn't work mathematically. This is not a differentiable function. It doesn't help too much with the math, doesn't help with regression and so on and so forth. So we still do the distance to the mean, it's just a different average, not the arithmetic. This is the quadratic average as opposed to the arithmetic average. It's still an average, as in if everybody would have the same distance to the mean, this value would give you that distance to the mean, just like an arithmetic average. So we're gonna have this notion of standard deviation and variance. There's a bunch of formulas that are equivalent. And we're gonna have a different notion next time, which is, this works for numerical values, right? Like all the values I show you are numerical. The roll of the die, how many heads the coin has, what's the average grade on the meter, all these are numerical values. What if my random variable is colors or names? Suppose I pick a student and I have his name, or his race, or his, I don't know, language. Can I average those things? I cannot. So I need, but those variables have also a measure of variability in them. I need a different measure for those. That's what we're going to do next time.